Hi, and welcome to the second lecture video on decision trees. Right, so in the previous video, we saw this first algorithm for constructing decision trees based on this greedy approach, right? So basically we start out with a tree that's just a root, and then we repeatedly try to replace all the current leaves of the tree with the best possible decision stump, where decision stump is just a single tree that has one root with a question and two leaves. Okay, and you just try to replace all of them and use the best one that we find. Okay, so this is basically what we do here, right? Which results in an accuracy of 7/8. We get 7 out of the 8 points correct. Right, so building the tree is really just keep growing the tree until you run out of your budget of internal nodes. Each time you try, if you want to grow this tree, you would try the 3 leaves of this tree, try to replace each of them by a decision stump. So a single node that asks a question and 2 children beneath it, where you, of course, answer return the best possible label in the 2 different leaves. Okay, so maybe you could ask yourself, right, is this just splitting based on this accuracy that we did in the previous video, is this the best you can do, or are there other sensible alternatives that you could try out? Right. So one heuristic that seems to work really well in practice is to not actually do the splits based on accuracy, but based it on what's called the entropy. So let me try to introduce what this entropy is and try to motivate why this would be a sensible thing to use when doing these splits in the tree. Okay, so let's first sort of define the entropy. So let's say I have n training examples, n points, and they all have a label between 1 and k. Okay, so I have a set S that consists of n points, and they have k different labels. Right. Then I can count for each of these labels how many of the points that have the label I. Right? So we can call this number ni. Okay, and then we can also look at what is the fraction of the points that have the label I, which is just the ni divided by n, right? How large a fraction of all the examples of the points have the label I. So once we have these PIs, we can then define the entropy, I guess in this case of this set of labels S, as the sum here, right? So what you do is you sum over all the different possible labels 1 through k. You have a -1 in front, and you take the fraction of points with label I and multiply it with log the fraction of points with label I. Okay, so this is the entropy function, the binary entropy function when the base here is 2. So let's try to motivate it a little bit. Why would this be an interesting function to look at? Okay, and maybe just a special case to notice is that if the PI is 0, we define 0 log 0 to be 0. Okay, so the entropy originates in information theory, and it's often called the Shannon entropy. And what it really is a measure of how much uncertainty there is in the probability distribution, right? So if I give you a point from this set S, how uncertain am I about the label of this point? Okay, so let's try to see that this formula in some sense makes sense for this uncertainty, right? But basically the main message is if you have high entropy, then there's a lot of uncertainty about the label of a point drawn from this set. So let's just try to see. So one way to think of the entropy is that it's a formula that gives the expected number of bits that you need to write down to describe the label of a random element drawn from S. Okay, so if I draw an element from S, how many bits do I need to write down to tell you what this element is? This is where the formula originates. Now, if all the elements in S are the same, right, it means that there's one label I such that the fraction of points with label I is 1, so all points have label I, and for all the other points, the fraction is 0. Okay, so Pi is 1, Pj is 0 for I not equal to j. Then the entropy is, well, we have to sum over all the labels, take the Pi times log of the Pi and a minus in front, right? So we have a term that's 1 log 1, and then we have k minus 1 terms that are all 0 log 0. So we define 0 log 0 to be 0, so this term goes away. Now, log base 2 of 1 is 0, so this term over here is also 0. So the entropy is 0 when all the elements are equal, which makes perfect sense, right? If I know that all the elements are the same, then there's no uncertainty left in this distribution, and then I wouldn't need to write down any bits to tell you which label I got. You already know because they're all the same. Okay, so that's the intuition. And then the opposite extreme is when there are equally many of all elements in S. This is I guess the distribution that maximizes this entropy, right? So in this case, if we distribute the elements evenly among the k different labels, then the fraction of points with label I is exactly 1 over k, which means that the entropy, right, we have to sum over all these different labels, like k of them, each of them contributes 1 over k times log 1 over k. Okay, so the k's here, as you can see, cancel out. The minus moves inside the log, so this 1 over k becomes a k, resulting in an entropy of log k. Which again, if you think about this intuition up here, how many bits does it take to describe the label of an element drawn from S? If there's exactly k choices, it makes sense that I need log k bits to describe any one of them. Okay, so that's the intuition behind the entropy function, right? And then for two elements, just a plot of what the entropy looks like. It is maximized in a 50-50 distribution between the two elements, where the entropy is exactly 1 bit, which makes perfect sense, right? If I have to describe one of two elements, I need 1 bit to do it. And if you go to the extremes where you know that it's always a 1, for instance, always the first element that you get, then the entropy drops to 0. Okay, so this is the definition of the entropy function. Okay, so how can we use this when we are building these decision trees, right? So what we can do is we can also try to measure what is the entropy of these sets of points that reside in the leaves of a decision tree. Right, so if we look at a decision tree that we've built so far, for instance, the one that's shown here, we can go over all the leaves, right? So we can look at, for instance, the left leaf down here, the blue leaf, and let's say, okay, so SV could be the subset of points that end up here. Okay, so there are n points in total. Some of them end up in this leaf. These 5 points are the ones that we're looking at. So that's the set SV. Now, what we define now for such a decision tree is the entropy of the decision tree. So what we do is just we sum over all the leaves, we compute the entropy of this leaf, and then we weigh it by the fraction of points that end up in this leaf. Okay, so sum over all the leaves, compute the entropy in the leaf, and then we weigh by the fraction of training examples that end up in the leaf. Okay, so if many points end up in a high entropy leaf, then the entropy of the whole tree is going to be large, and otherwise it can be small. Okay, so the entropy of the tree is defined like this. So let's just look at this example tree here and just try to compute what is the entropy. So first, let's start by looking at this blue leaf and computing what is the entropy of this leaf. Right, so there are 2 classes, right? So we have to count how large a fraction of the points that fall in each class. So 1/5 of the point fall in the red class and 4/5 fall in the blue class. So the entropy, by just using the formula for the entropy, becomes 1/5 times log of 1/5 plus 4/5 times log of 4/5, and then you have to negate this value. You just plug this into a calculator, you get out 0.722. Okay, this is a number less than 1, which makes sense, right? Because there's only 2 classes, and in the completely balanced case, the entropy is going to be 1. You can do the same here on the red leaf, right? We compute what is the fraction of red points, that's 2/3, and there's 1/3 blue points, and you plug in 2/3 log 2/3, 1/3 log 1/3, and you get 0.918 entropy. Okay, so now we've computed the entropy in the 2 leaves, and the formula up here now says that we have to sum over all the leaves and weigh the corresponding entropies by the fraction of training examples that end up in each of the leaves. So if you look here again at the blue leaf, right, 5 out of 8 of the training examples end up here. And then so we take 5/8 and multiply by 0.722. Over here on the right, we have 3 out of the 8 training examples that end up here. We multiply it by the 0.918, and the final result is 0.796. That's the entropy of this tree. Okay, here's another tree. We could also try what is the entropy of this one. So over here in this leaf down here, right, it's a 50-50 split between blue and red. So the entropy in here is 1/2 log 1/2. So log base 2 of 1/2 is -1. So you get -1/2, -1/2. You have a minus in front, so you get 1. Okay. Down here, right, it's a perfect split. Everything is blue. So the entropy is just 1 log 1 plus 0 log 0, which is 0. And finally, this one up here, 2/3 log 2/3, because the 2/3 red points, and 1/3 log 1/3 blue points, and with a minus in front, and you get 0.918. Right, so these are the entropies of all these individual leaves. And then we have to weigh them by the number of points that end up in each leaf, right? So over here, 2 out of the 8 points end up in this leaf that had an entropy of 1. 3 out of the 8 points end up in the leaf down here with entropy 0, and another 3/8 of the points end up in a leaf with entropy 0.918, resulting in a final entropy of 0.594 if you compute this value here. Okay. So as you can see, 0.594 it's a better entropy, a lower entropy than the smaller decision tree here, right? Which makes sense. It seems also that this tree here has done a better job at splitting the data and classifying it. Okay. So that's the entropy of a tree. And if you want some intuition for why we weigh it with the size of each of these leaves, one can think of this formula as measuring, in some sense, the number of bits that you would need to describe the label of a random training point if I tell you which leaf it ends in, right? So basically, if I give you a random point, the chance that it ends up in this leaf is proportional to the number of training examples over n in this leaf. And if it ends here, right, you had to pay this entropy to describe it. So this is basically just telling you what is the expected number of bits I need in order to describe one of these training examples, the label of it, if I tell you where it ends. And of course, if the tree perfectly splits the data, if I tell you where it ends, I already know the label of it. So that's an intuition for why if you perfectly split, the entropy drops to 0. So it's a natural measure of how much uncertainty is left after I've used my tree to classify the data, to split the data. Okay. So with this intuition of entropy, we can go back and revisit this greedy algorithm, right? So if you remember the algorithm, right, if we have a budget of k internal nodes to include in our decision tree, then we started out by constructing a root that is just a leaf. And then we repeated k times, that we take all the leaves in the current tree, we test all the different features that we have, and all the possible split values for that feature. And for each choice, what we do now, instead, before we computed the accuracy that resulted from doing the split, this time instead, right, we compute how much does the entropy of this tree decrease if we substitute v with this decision stump where we split using this feature that we chosen and the value x. Right, so instead of just using accuracy as a measure, the resulting accuracy afterwards, we use the resulting entropy of the tree as our measure. And we want this to be as small as possible. The lower the entropy, the better a tree. And so it's just a different strategy. The only thing that we change in our algorithm for constructing decision trees is how we determine what is a good split, right? So we basically just use the leaf replacement that reduces the entropy the most. That's the strategy. Okay, and maybe just to see this, it's not immediately clear that it isn't the best strategy to just minimize the accuracy, right? Because it could sound like if I'm maximizing the accuracy, if I have a good accuracy, then I also have a small entropy, which is true. In particular, in the extreme case where you classify everything correctly, the entropy also drops to 0. But in fact, they're not always the same, these two. It can actually give different splits. So let's have an example just to see that indeed accuracy and entropy can give different splits when you're building your trees. So here we're just going to look at a one-dimensional data set just for simplicity. So that's just one feature. And let's say the training examples look like this, plotted based on this one feature, right? So these are the x coordinates of these elements, and the red elements belong to one class and the blue to another. So if we look at this, before we do anything, so we're just at the root, we can look at what is the current entropy, right? So if we look at it, well, 3 out of 10 points are red. So we get 3 out of 10 log 3 out of 10, and then we have 7 out of 10 points that are blue. So we have a 7 out of 10 log 7 out of 10 factor here, and this gives 0.881. Okay. Now, if we were to split this using accuracy, right? So we're trying to find the split such that if I pick the leaf labels optimally, I get the best accuracy. Then if you stare at this for a little while, you'll realize that the best split you can do is this one here, right? And return red on the left half and blue on the right half, right? Because the only 2 points that are misclassified is the blue one here and the red one in here. And no other split can do better. No matter how else you try to split, the accuracy will not get any better than 8 out of 10. Right? So this is really the best split if you're using accuracy. But let's see that if you're splitting based on entropy, you'll actually do a different split. So we can start by measuring what is the entropy of the tree if we actually did the current split here. So if we did the current split, right, we can compute the entropy in this leaf. 2/3 of the points are red, so 2/3 log 2/3 and 1/3 log 1/3 to account for the blue points, giving an entropy of 0.918. We can also go to the right child. There's 1 out of 7 points that are red, so we get a 1 out of 7 log 1 out of 7. Plus a 6 out of 7 log 6 out of 7 for the blue points. Plug this in, it gives you about 0.592 entropy. Okay. And remember, right, again, the entropy, we have to weigh it by the number of points that end up in each of the leaves. So there's 3 out of 10 points that end up in the leaf that had entropy 0.918. 7 out of 10 points end up in the leaf that had entropy 0.592. Computing this number, you get an entropy afterwards of 0.690. Okay, so that's the entropy if we use the split that is optimal with respect to accuracy. Let's now try to see that there's another split that actually results in a smaller entropy. Okay, so this is just the entropy calculation that's been moved up a little bit. And now let's try to consider this alternative split down here, right? So clearly this is worse in terms of accuracy, right? Because over here on the left part, you get an accuracy of 7 out of 10, or you get half of the points wrong, right? So 3 of them are misclassified, and over here you get all of them right. But let's try to compute the entropy of this, the split that you get here, right? So if we go to the left leaf, this is perfectly balanced between red and blue. So it's a half log a half plus a half log a half, which gives an entropy of 1 bit. And whereas on the right-hand side here, the entropy is 0, it's a perfect split. Okay. And now, so the entropy, we have to weigh them by the number of points that end in each leaf. So we have a 6 out of 10 fraction that end up here and a 4 out of 10 fraction that end up here. So the final entropy is 0.600. Because you can see here, right, the entropy reduced more using this second split than it did with the first split here. So this really shows that entropy and accuracy do not necessarily build the same tree. Okay, this gives a larger entropy reduction, and if you build using entropy, you would choose this split instead. Okay, so if one wants to say something about the difference between accuracy and entropy, then in some sense, the entropy strategy will prefer what we would call pure splits. So down here, I will make a split where one side becomes perfectly classified. And so this is kind of like what we would call a pure split. Right? And accuracy, well, of course, focuses on accuracy. And it seems, at least, if you run these things in practice, when you construct decision trees, in particular some trees that are larger than just stumps, this splitting based on entropy actually seems to work better and give better results in practice. Right, so what we just saw, right, was that there was actually 2 different ways of trying to build this tree, right? One of them was, that we tried to get a good accuracy, and the other one was we tried to minimize this entropy of the resulting tree, right? And in general, right, it's not necessarily constrained to just these 2 things you could try to optimize when you're training a machine learning model. In general, there could be many different objectives that you would like to minimize, right? So let's try to look at an example that kind of motivates what we call loss functions. Right? So maybe one example you can think of is that CIA uses a fingerprint scanner at the entrance to some secure facility, right? And if this is the case, right, and you want to do some machine learning to figure out you want to implement this fingerprint scanner, and there are 2 classes, right? When you put your thumb on the scanner, it has to determine whether you're authorized or unauthorized. And of course, right, we've collected a lot of data that from individuals that are either authorized or unauthorized to construct this fingerprint scanner. Okay, so right, the idea is we want to train a model that can recognize whether you're authorized or unauthorized based on your fingerprint, and you should do this using training data. Now, one thing here to be aware of is that if you're training one of these models, right, normally you're just counting how many misclassifications that you're doing in binary classification, right? In all the examples we've seen, we're just maximizing the accuracy. But in this example here, right, it's clear that it's significantly worse if I allow an unauthorized person to enter the building than if I happen to deny someone who is authorized, right? Because that person that is authorized can probably just call the supervisor, and maybe someone can come and open the door, let them in, do a manual scan or verification that this is indeed an authorized person. Whereas if you actually let someone in who's unauthorized, you don't know what they could do. So here, clearly, it should not be the same, what you can call priority between not authorizing someone who's unauthorized and vice versa. So what you could do with this in this example is that we can define what we call a loss function. Okay, so a loss function is a function that somehow determines what we should pay when we say misclassify a training example. So a loss function takes 2 arguments, the predicted label and the true label. And what it does is that it just assigns value to any combination of the 2. So for instance, in this example up here with the CIA and the fingerprint scanner, right, you could say, okay, if I happen to authorize a person who is authorized, or I deny a person who's unauthorized, then I don't have to pay anything, right? I did it perfectly, right? So I don't pay anything, I pay 0, the loss is 0. Now, you have this, then on the other hand, if my prediction, this is the first argument here, is this person is authorized, the true label is unauthorized, right? This is the really bad example, right? We're saying that someone who's not authorized is actually authorized. We're letting someone into the building that we shouldn't. This should be super expensive. So we can say that, okay, maybe the cost here is 1,000, right? It's much more expensive to say that someone is authorized if they're not authorized. On the other hand, right, we could assign a loss to the opposite case where you have someone who is authorized. That's the second argument here, the true label. But you say that this person is unauthorized. Maybe you could say that the loss here that you have to pay is only 1, right? So you can define your function to capture, what are you interested in this application. And now what you would like to do in supervised learning now, when you have such a general loss function and some training data x1 to xn with labels y1 to yn, is that you would like to find a hypothesis that minimizes the loss on the training data. All right, so before we just looked at minimizing or maximizing the accuracy. Here we're looking at minimizing the loss that we have to pay, right? So you sum over all the data examples, you look at the true label is yi, the prediction here is what your current hypothesis predicts on xi, you evaluate what is this loss, and here we're just averaging over all the n training example, right? So basically we're finding the hypothesis with the smallest average loss on the training data, right? And then the basic idea and intuition is similarly to before when we were hoping that high accuracy in training data implies high accuracy in new data. We're hoping also that if I have a small loss on my training data, I'll have a small loss when I get new and unknown data, at least if it's true that this new data looks a lot like the training data. Okay. So let's just see that this, in all the previous videos, we looked at mainly maximizing the accuracy, right? We want to get as many things correct as possible. Let's just see that this can be captured by minimizing a loss instead. So basically maximizing the accuracy is the same as minimizing what's called the 0-1 loss. So the 0-1 loss is just the following, right? So if I make a prediction for a label y prime and the true label is y, then I pay 1 if the prediction is wrong, and otherwise I pay 0, right? So basically I'm paying for all the mistakes. So clearly minimizing the number of mispredictions is the same as maximizing the number of correct predictions on the accuracy. Okay, so really we can think of everything that we've been doing so far as just minimizing the 0-1 loss over the training data. Good. So for these decision trees that we built, when we built them greedily, basically what we should do is when we're in the leaves and we've chosen any desirable loss function, we have to return a value in this leaf, right? So what the best we can do is to return the label that minimizes the loss, right? For any given loss we've chosen, if I have a leaf, I should just return the label that minimizes this loss on the training examples that end up in this leaf, right? And then we can just run the same algorithm, try all the splits, look at, for every leaf, we figure out what's the best value to return, and we can look at what is the loss for each of these different trees. So let's try to see that in action if we go to regression instead. Right, so if you remember, regression instead of classification is that we have to predict a value, in this case a real value, instead of a class or category. Right, so the labels now are real numbers. So the running example was this: predict the price of a house. Okay, so a very popular loss function when we're looking at regression, so predicting real values, instead of this 0-1 loss, right? You don't want to pay 1 if you're wrong and 0 if you're correct. What we do instead is what we use often what's called the least squares loss. So the least squared loss is just the difference between your prediction and the true label squared. That's the least squared loss. So for instance, right, if I were to predict the price of a house and I make a prediction of 5.3 million, but the true value of the house was 5.15 million, then the least squared loss, the mistake I have to pay, is 150,000 squared, like the difference between the two numbers squared. And here, right, you can see that it makes sense. If I try to use the 0-1 loss, I would have to pay 1 here because my prediction is incorrect. But if I had predicted 10 million, the price would have been the same, right? 10 million is also just different from 5.15 million. So if I'm just paying 1 whenever I'm wrong, I wouldn't be able to say that this is at least a better classification or prediction than predicting 10 million or 100 million. So here's a loss function that makes sense, at least this least squared loss, when we're looking at regression problems. Okay, so if we go back to this greedy algorithm, let's try to use this greedy algorithm to build a regression tree. So how to predict values instead of labels. So again, if we look at the training data right now, the labels are not a class, but instead they're values, right? So basically this point here has a value of 2, the label is 3 in this case, 10, 11, and 9. So what we'd like to do now is build a decision tree such that when given a new data point, we can hopefully predict the label well. And again, the way we do it is that we try to minimize the least squared loss on the training data that we have here, right? So we want to build a tree that if we evaluate its predictions on these training examples, then the least squared loss, so the sum of all the points of the squared difference between the prediction and the true value, that sum has to be minimized. So what we try to go back and see how we derive this greedy algorithm, right? What we started by looking at is, what if we just have a leaf? What values should we return? What is the best choice? So again, right, if we have a leaf, it has to return a value now. You don't have any more questions to ask, so you have to output some value x. Now you can look at, if we return the value x, then what does the loss become on this data here? Well, the loss, right, is the average over all the points of this least squared loss that we define to be the difference between the prediction here, x, and the true label yi. Right, so this is the loss that we have to pay. If we go over all these training points here, we'll basically, okay, if I return x, then on this point here, my mistake is 2 minus x squared. That's my loss. The contribution to the loss here is the difference between 3 and x squared, the difference between 9 and x squared, 10 and x squared, and 11 and x squared. And then I have to average over the 5 training examples. So this is the loss that I would have to pay if I happen to return the value x. And of course, if I just have a root, I should, of course, choose the value x that minimizes this loss, right? So I just want to choose x to minimize this sum of squared differences. Okay, so then you can ask yourself, what is the value that minimizes this sum of squared differences? Right. It turns out, and this is a rather simple exercise, you can prove that the x that minimizes such a sum of squared differences, the average of the sum of squared differences, is just the mean of these yi's, right? So you just have to return the average value of all these labels, right? So you sum over all the labels and you take the average of it. Okay, so this can be proved that the best value to return to minimize this squared loss is just the mean. Which means that for this training data that I have up here, right, if I were to return a value in this root, I have to pick the mean. So the mean, right, you sum up all the values, 2 plus 3 plus 9 plus 10 plus 11, and you divide it by 5. If you sum these up, you get 35 over 5, which is just 7. So the best value you can return is 7. And now if you return the value 7, you can compute what is the loss, right? So you sum over all the points again, 2 minus 7 squared, 3 minus 7 squared, 9 minus 7 squared, 10 minus 7 squared, and 11 minus 7 squared. And then you take the average of all of this. And if you compute this, you get 14. Okay, so this is the loss for using this root value here. Okay, so now what could we do if we were to build, this is a regression stump, I guess it's called in this case. So a regression stump is similar to a decision stump. It's just you have a single root that asks a question, and then you have 2 children that are leaves. And of course, right, if you want to choose the best root, the strategy is the same as before, right? We try all the different features, and for every feature, right, there's n-1 relevant splits between all of the points. And so basically what you can do is you can just try all the splits on all the features. For any given one of them, you know which points end up in which leaves. And when you have such a split, right, you know that in the leaves, you should just return the mean of the elements that are there. So let's try to do it here, right? So let's say that we're testing this split now. Now, this is a valid split. Is feature B less than or equal to 6? Okay, and what we do now, if we make this split, you can see that, in the left child here, the elements that end up there would be 2, 9, and 11. And in the right child, the elements that end there would be 3 and 10. So to test the split, we need to figure out what is the best value to return in the 2 leaves. So we have to return the mean, right? So the mean of 2, 9, and 11 is 7.33, and the mean of 3 and 10 is 6.5. Okay, so now we know these are the best possible leaves if we choose this split. And then we can just evaluate what is the cost here, what is the least squared loss. So we have to again sum over all the points. We look at the true label, say 2, minus the prediction 7.33, and we have to square it. We also have the 9 minus the 7.33, we have to square that. And then we have the 11 minus the 7.33, we have to square that. And then we have the 2 points that end up in the other leaf. Here it's 3 minus 6.5 squared and 10 minus 6.5 squared. And then we have to average over all 5. And this just, if you plug in the numbers, this gives you 13.833. Okay, so this we've actually evaluated the quality of this split, right? This results in a final loss of 13.833. We could also test this split here, like this vertical split here. This looks a little better if you just look at it, right? Because these numbers over here on the left are closer to each other, and these numbers over here on the right are closer to each other. And indeed, right, if we do this split, say for instance, feature A is less than or equal to 4, then over here on the left, you will have 2 and 3 that end up in this leaf, and over here you have 9, 10, and 11. So the mean of 2 and 3 is 2.5, and the mean of 9, 10, and 11 is 10. So we can also check what is now the least squared loss for using this decision tree. Right? So we sum again over all the points. We have the point that has a label of 2, but we predict 2.5. This difference is squared, so this is a quarter. 3 minus 2.5 squared, that's another quarter. So this gives us a half. And now what we have here is 9 minus 10 is 1. Squared, that's 1. 10 minus 10 is 0, and 11 minus 10 is 1. Also when you square it. So we have 2 plus a half, so there's 2.5 in here. 2.5 divided by 5, that's just a half. Okay, so the least squared loss for this split is a half, whereas the previous split that we saw here had 13.833 as its loss, right? So clearly this is a better split with respect to this loss function. And this is the corresponding tree, right? So this is the best split you can create. Right? Of course, you have to test all of them, but clearly this is the one that's going to be the best. Okay, so this is how we can now build these regression trees. So basically, we just take the greedy algorithm that we knew before, and if we have this budget of k internal nodes, we start with the root, that's the leaf, and then we repeatedly look at all the leaves, try to replace them by a regression stump. And we do this by trying all the possible splits and all the possible, for all the different features, and computing the best possible leaves that are there. And then we just evaluate how good is this tree by looking at what is the loss function. What does it evaluate to if this is our choice, right? So in summary, right, in these 2 videos, right, we introduced decision trees as an alternative hypothesis set to these linear models, right? And we also saw, basically, we showed how you can construct leaves and decision and regression stumps optimally, basically just by trying all the possibilities for the splits, and then just computing the optimal value to return in the leaves, right? And this greedy approach works also for then we can combine it with this greedy approach to build even larger trees where we just repeatedly replace a leaf by a decision or regression stump. Okay. We also saw this entropy-based construction where we're trying to minimize this entropy in the leaf, right? It's a different loss function, right? So loss functions, we saw that the previous one where we're maximizing the accuracy is the same as minimizing the 0-1 loss. So just minimizing the number of mistakes you make, we just pay 1 for every mistake. And we saw this least squared loss for regression problems where the penalty you pay for making a mistake in your prediction is the difference between the prediction and the true label squared. And then we saw how to construct these regression trees basically using this greedy algorithm and the least squared loss, right? So just use the greedy algorithm, use the least squared loss to evaluate the quality of these different trees, right? Good. That's it.